4 class days. So we have 3 more class days before the exam. I think we'll just do chapters 3 and 4 on that exam. So you have a couple of projectile motion problems, or maybe a projectile motion problem and a vector problem, or maybe a vector problem sort of framed in the sense of forces, like where I give you a series of forces and ask you what is the equal but opposite force. We'll work a problem like that today. You'll have an inclined plane with at least two bodies on it, with or without friction. We'll work through some problems like that today or Wednesday. But you should be in a pretty good position by Wednesday to spend the break. I don't want you to spend the break studying, but if you want to do that, you should be in a good position now to be studying this week. Okay? Have any questions about sort of what we're doing this week or into next week for the exam? I'll set aside half the class on Monday for just questions that you have as you're preparing. Is there any big news from the weekend? No? Okay. Not much for us either. All right, let's continue on. We did Newton's first and second law. Remember, the first law was the law of inertia, that objects tend to stay in the state of motion that they're in already. And then the second law was the law of acceleration. The law of acceleration was just that F equals ma. And then the third law is, I don't know, people call it different things, but typically it's like action-reaction. The law of action-reaction, if you will. Whereas if you have a force, then you have a reactive force, that you have an equal and opposite force. So if objects 1 and 2 interact, then the force F12 exerted by object 1 on object 2 is equal in magnitude but opposite in direction. Opposite in direction. This comes up with contact forces. Anytime you have a contact force, right, like if you're in a fist fight or whatever, that every time that you hit somebody, that they push back on you with the same force. All right, so anytime, this is obviously true for a contact force. For example, if I push on the wall with a certain force, the wall is going to push back on me with that same force. So we would call this then the force of object 1 on object 2. Like if I'm pushing on the wall, where object 1 is my hand, object 2 is the wall, and then this would be the force on object 2 due to object 1. That is just the object pushing back on us. Let's see, we see this also in field forces as well. And next semester at the very beginning, we'll have a whole chapter on the gravitational forces again. We'll sort of revisit it and look at how we calculate the field and how we work with the field. And there's some interesting mathematics that comes up. But just for now, know that like if we have a field force, say an object 1 and an object 2, M1 and M2, that they experience equal but opposite forces. So this would be F12, the force on object 1 due to object 2, and then this is F21. Let me write this in words just so you know those subscripts means. The force on object 1 due to object 2. Due to object 2. We see this in electric forces as well. Any kind of field force, any force at all actually, any contact force or any field force. And so the result of this law, which is uh, actually pretty profound, is that no isolated force exists. That if Newton's third law is correct, that for every force you have an equal and opposite force, then there can never be an isolated force. That if you have one force, then you're always going to have an equal and opposite force that will exist. And we know that's true for contact forces because, like I said, when you have a force that's exerted on one body, then that same force is going to be exerted back on the originating body. And then also it's true for field forces as well. Um, This is also true. They sort of, Derek in that video, in that Veritasium video, he sort of addressed this a little bit, that if you have a big object exerting a force on a small object, it's our tendency to think that the big object exerts a big force and the little object exerts a small force. But that's not true, right? This is not a correct statement. Uh, Imagine that we have the sun. That's the sun. And then we have the Earth, which is really small. These exert the same forces on one another. So the Earth is exerting a force on the Sun, and the Sun is exerting a force on the Earth as well. The same is true for the moons. And this whole idea, these forces, these gravitational forces, and the fact that they're equal, that's what goes into Kepler's laws. If you ever take astronomy, you'll get into Kepler's laws. Have y'all taken astronomy here? No, it's a good course. I know y'all don't need to take it, but it's a fun course if you're interested in anything like that. They get a little bit into Kepler's laws, do a little bit of the physics of orbits, but then just talk about sort of how the orbits affects things like lunar eclipses and solar eclipses and all that jazz. It's actually kind of fun. All right, what about the force due to gravity exerted on you by Earth? Is that an isolated force? Right, so I weigh how much? Y'all know? I told y'all this, right? About 700, not 700 pounds, but 700 newtons. I weigh about 700 newtons. And so that means that the Earth is pulling down on me. This is the Earth. This is me. The Earth is pulling down on me with a force of 700 newtons. So what is the action-reaction force for this? What's the reactive force for this 700 newtons of weight? Right, I'm pulling back. So the Earth is pulling down on me, but I'm pulling back on the Earth with 700 newtons. Every body exerts a force on, every body of mass exerts a force on other bodies of mass. As I said, contact forces also obey Newton's third law, and the result of this is the normal force. This does not mean normal as in usual. Right, that's not what it means. What does the word normal means in a mathematical sense? Have y'all heard this? Right, it's perpendicular and in the same plane. Yeah. Yeah, so we're not really worried about the plane, but we'll just say that it's perpendicular because we're only going to be dealing in 2 dimensions anyway, so we'll always be in the same plane. But it does mean that it's perpendicular. Perpendicular. All right, so the normal force will always be perpendicular. Um, so for example, if we have an object on a table like this, there is a force due to weight that's acting on the object. That's just the weight of the object, the mass times the gravity. Let's say that it's 10 kilograms. That means that the force weight is 100 newtons, 10 times 10 meters per second squared. And the normal force, as a result, is also 100 newtons. So the normal force is equal to 100 newtons. By the way, the system by which we get to that, which will be, it's not really terribly important here, but it will be important when we get to more complicated problems, is that we draw all of our forces as we've done here, then we apply Newton's second law. The sum of the forces in the y direction is equal to ma times y. We recognize that the acceleration is 0, so the sum of the forces in the y direction is 0. Then we say Fn minus Fw equals 0, and so Fn is equal to Fw. That should seem fairly obvious to you here, right? It does seem obvious that if these two vectors are equal, they have to, or if they're opposite one another and they add up to equal to 0, then they should be equal but opposite. It's obvious? Okay, maybe not, maybe. But this technique where we draw the vectors, draw the forces, we apply Newton's second law, and then we solve whatever equation we create by applying Newton's second law. That'll be sort of our standard framework for solving these problems. Okay, so sort of keep that in mind as we move along, because that framework, while I said it's not important here terribly, it will be terribly important when we get to more complicated problems. Okay, let's see. So that's just going to work it here. Now the normal force isn't necessarily equal to the weight of the object. As I said, the normal force is always perpendicular to the surface. And sometimes we will get normal forces of objects on inclined planes, and you will have an inclined plane problem, a two-bodied inclined plane problem on the test. You have several variations of that in the homework and the old test questions, and we'll work through some of those here. But you just need to be well versed on that. The normal force is always perpendicular to the surface. So for example, here, if I have a block on an inclined plane, I have the weight, which is always towards the surface of the Earth. The inclined plane, the way it's set up, the normal force now will be like this. Often students will instead draw their normal force like this. That is not correct. But I think you're just so used to having the surface be horizontal that you just always draw your normal force up. But that is not necessarily the case. The normal force does not have to be up. In fact, when we get into equilibrium statics at the end of the semester, we'll see problems like this where you have, like a ladder or something that is leaned up against a wall. Then we'll find that the normal force in this case is in this direction, right? It's off to the side because it's perpendicular to the surface, or it's in this direction because it's perpendicular to the ground. So we'll see problems like that later in the semester where our normal force is not uh, vertical or not, or not vertical rather. All right. Um, I want to actually use this space up here to work a different problem. Let's say that I have an object, say that I have a block, say that it's, we'll say it's 10 kilograms, and I'm pulling on it in this direction with a force equal to 20 newtons at an angle of 30 degrees. And I want to know what is the normal force acting on that block. What is the normal force? All right, the first thing I want to do is just label all my forces. I have a force that's not labeled here. What is it? I have the weight that's not labeled. So the first thing I want to do is label my forces. I'm just going to write our little steps here. Label the forces. All right, the next thing that I want to do is draw a coordinate system. We didn't do that before because it was obvious what our coordinate system was because we were only in one dimension. So here I'm going to draw my coordinate system. I'm going to draw it like this. All right, with the assumption that this vector comes back to the thing. Let me redraw these vectors in blue. So I have one vector there that's at an angle of 30 degrees, and then one vector that's there. The next thing that I want to do after I draw my coordinate system is I want to resolve my vectors. I'm going to draw a new coordinate system, just sort of redraw it. Now I have on this axis, I have 20, what, cosine or sine? Sine of 30, right? Over here, I have 20 cosine of 30. And then on here, I have the weight, which was 100 newtons. All right. I have another force, actually, that I haven't drawn. What's the other force that I haven't drawn? What is it? The kinetic? No. A little bit heavier. We don't have any friction. He's talking about friction, which we haven't gotten to yet. What's the force I haven't drawn? I have the force being applied. That's just a force that some guy is pulling on it. That's the 20 newtons. Then I have the weight. And then I have the normal force, right? So my normal force points perpendicular to the surface. So I'm going to draw it right here. So I've resolved the vectors. Third step. The fourth step will be to apply the second law. And then the fifth and final step will be to solve the equations. Once you get up to the fourth step, you're basically done. But you might have a bit of algebra uh, in the fifth step, solving the equations. And actually, we're going to use a matrix method to solve the equations later, which you can do on your test for extra credit. Some of you might have done it before. All right. Now I get two sets of equations. I get the sum of the forces in the x direction and the sum of the forces in the y direction. In this case, in the y direction, the object is not moving at all, and our acceleration is 0. In this case, it turns out that it is moving in the x direction, so I'm just gonna have max. Often on our problems in the y direction, we'll have acceleration to be 0, but you'll just have to take that on a case-by-case basis. All right, so the sum of the forces in the x is just 20 cosine 30 equals m, which was 10 kilograms, times ax. So if we wanted to know the acceleration, we could find it. But really, I'm just looking for the normal force. I'm going to do that over here. The sum of the forces in the y direction is going to be Fn plus 20 sine of 30 minus 100 equals 0. So Fn then will be 100 minus 20 sine of 30. What is that? 100. Oh yeah, of course, it's 90 newtons. Okay? So that's the procedure that we'll follow on all these problems. And as we get along, we'll start to see that the equations, mainly it's just that the equations are going to be harder to solve. Uh, but largely this is it. Sometimes if you have two bodies, instead of just having two equations, then you'll have four equations. For every body that you have, you'll have two equations, one for the x direction and one for the y direction. And sometimes one of those equations might not tell you anything at all, or sometimes it might be sort of the key to solving the problem. All right, but this is the procedure that we'll follow each time. Let's see here. Let's look at this inclined plane. I want to first just sort of point out a few things. I sent out a YouTube clip last week. Did I send it to y'all as well about the sort of hints about the inclined plane, basic stuff about the inclined plane? No, I'll send it to you. It's just we hadn't gotten to it yet, so I don't want to bug you with it. Um, Hold on just a second. Let me send myself a note just so I don't forget. It was just a video sort of outlining some of the basic stuff about inclined planes. So first of all, one of the things that you need to recognize on an inclined plane is it's very important to choose your coordinate system correctly. Often, people will take a coordinate system that looks like this. Don't draw that, because I want to show you why it's wrong to draw it that way. Or not why it's wrong. Like, you can choose whatever coordinate system you want, but if you have an object that's moving, if you have an object that's moving on an inclined plane, this coordinate system is going to give you difficulty. Why does this coordinate system give you difficulty if you're moving on the inclined plane? Now, remember, when we're choosing our coordinate systems, we want to choose them so that more of our forces are on the x or y axes, or more of our vectors are on the x or y axis. So as I have it drawn here, right, you would say, well, the weight is in the vertical direction, so why not choose this coordinate system? Because it puts our weight on the y-axis, and our normal force is not on the y-axis, but you know, who cares? But why would this particularly make it difficult to solve a problem like this? Yeah, Cody? E- Exactly right. So our motion will have two different axes. When we go to find our acceleration, we'll have both an acceleration in the x direction, and we'll have an acceleration in the y direction, because our acceleration will either be in this direction or in this direction, and we'll have x and y components for both our accelerations. And that means when we write Newton's second law, neither one of those are going to be equal to 0. So we have two unknowns. It's going to make it quite a bit more difficult to solve. Not impossible to solve. I mean, either way you'll be able to solve it, but more difficult to solve. So we want to make it as easy as possible. And in order to do that, we'll draw a coordinate system like this. when we're doing inclined planes in this class, we'll always draw a coordinate system like this with our x-axis here and our y-axis here. Okay, so always draw your coordinate system like that. And also remember that the normal force is always perpendicular to the surface. And those are sort of common mistakes that people make. Um, the other thing is that when you're finding the force or the angle for the weight, let's say, for example, this angle is 30 degrees, I always measure my angle with respect to the x-axis. So if I draw this coordinate system over here, and then I go back and I label my forces, I have my normal force here, and then I'm going to draw my force weight here. What is my angle of that force with respect to the x-axis? What is the angle? I have this vector, this weight vector right here, and I want to know what is this angle. Now I know the angle of the inclined plane is 30 degrees, but can you see something about this arrangement that would tell you what this angle is here? It's going to be 60, right? Because notice that you have a triangle here. I'll outline it for you. I have a triangle, a right triangle, right here. So if that angle is 30 degrees, that means this angle is 60 degrees. Now it's also true that this angle is 30 degrees, so you can either measure that from the x or y axes, but let me tell you, I always measure it from the x-axis. It just makes it a little bit easier, because when I write the x component here, I can say FW cosine 60, and I can use that cosine, which is sort of the standard way of doing it, that we've been doing it. And when I write the y component, I can say FW sine of 60. But notice that it would be just as correct for me to say FW sine of 30 and FW cosine of 30. Both of those are true because the sine of 60 is equal to the cosine of 30 and the cosine of 60 is equal to the sine of 30. Okay? Just be careful of that because students sometimes make mistakes with that with their angles and finding their x and y components. And then also if you look back on some of the old tests, I used to not teach it this way. I used to have the students use this angle, and so you might see these flip-flops sometimes. That for the y component, I say, oh, it's cosine. That means it's the cosine of this angle, not this angle. Notice that this side right here, the y component, is adjacent to the 30 degrees. So that's why it's the cosine. It goes back to our definitions of cosine and sine. Okay? So the coordinates, your normal force, make sure it's perpendicular to the plane. And then the third thing is that angle. Make sure that you do 90 minus the incline angle when you're working these problems. 90 minus 30 in this case to get the angle for the weight. Okay? There's a little video sort of outlining those hints, and those are sort of common mistakes that students make on the inclined plane. Oh, I just gave it to you. Yeah. Often on an inclined plane, that angle is given, almost always. All right, let's work a simple example. As I said, when you have a problem on the test, it'll be an inclined plane with two blocks. Variety of ways to do that. I guess it could be one block, but likely you have two blocks, which will give you more of a system of equations to solve. But let's look at this one. I just want to know if I have a force acting along this plane in this direction, what must that force be so that the block is stationary? So I'm going to redraw it. This is a 10 kilogram block. This is 30 degrees. I'm going to draw my coordinate system. There's my x-axis. There's my y-axis. Now I can draw my vectors. I have the weight, Fw. Remember, this is 60 degrees. I have my normal force, Fn. And then I have some force, F. And I want it to be such F, such that this whole thing is stationary. So I've drawn my coordinate system. I've labeled my forces. Now let's resolve those vectors. I just discovered the pink dashed line. How do y'all like that for a coordinate system? I think it makes a nice coordinate system. All right, so I have my normal force, have my force F here, and then I resolve those vectors. I'll go and resolve them for the force weight. And then go ahead and start to apply Newton's second law. So remember, Newton's second law is the sum of the forces in the x direction, and then the sum of the forces in the y direction. So go ahead and resolve your vectors. Then you should have vectors that are clearly in the x direction and vectors that are in the y direction. And then you want to apply Newton's second law. So you'll have two equations that you'll apply from that. You might feel like you don't really need to write out the equations on this, but I really recommend that you do. The equations are pretty simple in this case. I recommend that you do write them out just to get in the practice, because on your test they'll be a bit more complicated and you'll want to write them out just to make sure that you're careful. All right. Now we want to ask ourselves the question is, what is the acceleration? So I'm going to write the sum of the forces in the x direction. Hopefully you've already done it. Is equal to max. And the sum of the forces in the y direction is may. What's the acceleration of this object? I want to guess. Give an answer. Well, this object is what? Is it moving or is it stationary? It's stationary, right? So this is a static problem. That means that the acceleration is going to be 0. So for both of these, my acceleration is 0 in the x and the y direction. So I can just set both of them equal to 0. I can say Fw cosine 60 minus F equals 0. And I can say Fn minus Fw sine of 60. That's also equal to 0. So if I want to know F, all I really have to do is solve this. I just say F is equal to Fw cosine 60, which is what, 86 newtons? That's Fw is 100. Oh no, sorry, it's 50 newtons. 100 newtons times a half is 50 newtons. Okay? It turns out that we didn't need the second equation, but we'll get into friction, and you will need to find the normal force because it turns out that the friction is dependent upon the normal force. We'll get into that soon, probably today. All right? Remember, we follow those steps. Let me step through it again. Draw my coordinate system, label my forces, note any angles and label what those angles are. Resolve my vectors and lay them out on a coordinate system. If you have two blocks, by the way, you'll have two coordinate systems, and so you'll just repeat this step. So you have two diagrams. This, by the way, is called a free body diagram, where you label all the forces on the object. Then I apply Newton's second law here and here in the x and the y direction. And if you have two bodies, then you're going to have two sets of equations like this. So you'll have 4 equations total. Um, and then I just solve whichever equation I need to find the value that I need. Or I might have to solve a system of equations, as you'll likely have to do on your test. Okay? Y'all could do this right now if I gave it to you. Steps are pretty simple. You're really just dealing with vectors here, so there's not a whole lot of new stuff here. It's just this idea of applying Newton's second law. And then we're going to be solving systems of equations, which is always a little hairy for students. But you can do it, I know. Let's see. Let's work a different problem. How do we want to do it? Yeah, let's say that we have an inclined plane. We'll do 30 degrees again. Let's say that I have a block here, and that the mass of the block is 10 kilograms. And I have a force acting on the block. Like this. I have that force acting on the block, I'll call it F. And let's say that F is let's say that F is 200 newtons. Right. I want to know what is the acceleration. This force acting on a block, I want to know what is the acceleration of the block. It's going to obviously be going in which direction, up or down the inclined plane. It's going to be going up the inclined plane. First step that you want to do is just to label all of the forces. All right, so there are several forces that aren't labeled here. Or there are a couple of forces, rather. What are they? Right, the normal force is 1, so I'm going to go ahead and label it. Now listen, we know that our forces actually act at the center of the body, but I'm going to label them there, just acting so they all vectors sort of come together there. And then I have another force acting. What is that? Right, I have the weight of the object, FW. I'm going to draw my coordinate system. Let's see, I'm going to draw these in blue here so I can see them better. And draw my coordinate system. Oh, I'm sorry, that's the wrong coordinate system, right? I'm going to draw my coordinate system like this. Now in this case, it's actually going to have two vectors that are going to be off axis, but we'll deal with it. It's still better to, more beneficial to have our acceleration vectors, one on be 0 and one not. All right, so now I need to work with my angles a little bit. I'm going to go ahead and draw these on a separate coordinate system over here. If I draw my normal force, it's right here. I know what my force weight is. Hopefully this just sort of becomes natural to you. This is going to be FW cosine or sine of 60. Cosine of 60. And notice that I did not use this angle, that I did 90 minus that. This will be sine of 60. Hopefully everything to this point is just sort of natural for you eventually. That, because you know you're always going to have normal force, you're always going to have the weight. It's going to be that other force that'll be a little bit different. All right, now I want to find the x and y components of this force F. What is this angle right here? Let me draw two parallel lines. This is a little geometry for you. If I have two parallel lines, and I have a line that goes in between them, this is my 30-degree angle. That's this angle. Now I'm looking for this angle. What is it going to be? It's also 30. Notice that in this diagram that's this angle right here. Let me draw over it with yellow. These are my two parallel lines, and then this is the line that goes in between them. And so this angle is equal to this angle. You'll get the hang of this, okay? I know it's been a long time since you've had geometry, but you need to get the hang of sort of seeing these various angles as they're laid out. So now I need to find the x and y components of F. I have an x component, and I have a y component. I'm going to draw those on my vector diagram. So here I have F, what's it going to be? Oh no, I'm sorry, that's not it, is it? Where's my y component? Is it positive or a negative y component? It is negative. Let me go ahead and draw that vector F. So my vector F is here, and I have an angle that's 30 degrees. That's just drawing this vector. Notice I've rotated my coordinate system. That's why it looks a little funky. You with me on this, folks? Yeah? All right, now I want to find my components. I'm going to do them on the same coordinate system. So I have F cosine 30, and I have F sine 30. Okay? So I want to know what is the acceleration. Which am I going to consider? I might not always need the x and y axes to apply Newton's second law. I mean, I could do that here, but I'm not going to need to. If I want to find the acceleration, I know the acceleration is in which direction, the x or y direction. It's in the x direction. So which of the axes will I consider to find the acceleration? I'm just going to use the x. And it turns out here that I don't need the y-axis, so I'm not even going to write that down. But if I want to know the sum of the forces in the x direction, that's going to equal my max It turns out that AX is the only acceleration I have, so it's going to be FW cosine 60 minus F cosine 30. That's equal to the mass times the acceleration in the x direction. See, I can put some values in here. My mass was 10 kilograms, so this is going to be 100 newtons cosine of 60 minus 200 newtons cosine of 30 divided by 10 kilograms equals AX. I get negative AX is negative 12 meters per second squared. Notice that it's negative because the acceleration, as we know, is going to be up and in this direction, just because that's the way the force is pulling it. And so that's going to cause it to go in the negative x direction, which is on this axis, the negative x. All right, but we might just record this as 12 meters per second squared up the inclined plane. I think you have a homework problem that's similar to this, if I'm not mistaken, but it includes friction. And friction makes this a lot more complicated because then the friction is dependent upon what's going on in the y-axis. We'll get into friction soon, but the friction is dependent upon the normal force. So still a more difficult problem, not quite the same difficulty you'll see on the exam, but getting closer. Still the same procedure. I draw all my forces. I select my coordinate system, but for the inclined plane, your coordinate system is always going to be with the x along the plane of the incline. I resolve my vectors, and then I apply Newton's second law. That's pretty easy, right? Same procedure every time, exactly the same. All right, let's try this quick test. In this case, I give you, actually, I'm going to zoom in. You don't really need the instructions. Here I give you three forces that are acting on an object. Your normal force is right here. And I want you to tell me which of these equations is correct. So three of these equations are incorrect, and one of them is correct. And I want you to tell me which of these is correct, excuse me. That is, from applying Newton's second law to this inclined plane, which of these equations is correct? Notice here, by the way, this is an older test question, but that I use both 30 degrees and 60 degrees. Remember sort of what happens there when you use the 30 degrees, that your sine and cosine are flip-flopped. You want to draw your coordinate system. You want to label your angles, resolve your vectors, and then you can tell which equations are correct or incorrect. Or you might just be able to look at them and sort of reason out which of these are correct or incorrect. Some forces are obviously not related to other forces because they're not acting in the same axis. Alright, let's see. We'll go about 15 more seconds. Stop at 245. 245. It looks like y'all are sort of split between B and C. Looks like C is the right answer. Uh, you can see that B is not the right answer by a couple of things. Some things that might want to key you off on this. First of all, notice that on B, that Fn is listed there, and then also AX is listed there. All right, but the normal force acts along the y-axis, and AX acts along the x-axis. So that should be the first thing that keys you off that this is not correct. FW sine of 30 also, this is, FW sine 30 is the x component of my FW. Remember, I could have FW sine 30 or I could have FW cosine of 60. Both of those are equivalent. And so this acts along the x direction, which again, the normal force always acts in the y direction when we draw a coordinate system like this. So that's what's going to get key you off there. For D, the weight is equal to the normal force. The weight and the normal force are related, but it's going to be a component of the weight, so it's going to be FW sine of 60 would equal to the normal force. And up here, Fn minus F is equal to 0. Fn is on the y-axis, F is on the x-axis. So these two forces are not related at all. So C is the right answer there. Fw sine 60 is equal to the normal force, and that is sort of the normal way that we would write that, because we would take this angle to be 60 degrees, and then the y component of Fw would be Fw sine 60. So we'd say the sum of the forces in the y direction equals MAY. That's Fn minus Fw sine 60 equals to 0. So it tells us Fw sine 60 equals Fn. So C is the right answer. You want to get practice on your inclined plane. Like I said, you're always going to have that normal force. You're always going to have that weight. So you should just be able to, as soon as you see it, you should know, boom, I know what the x and y components of my force weight are, and I know that my normal force is acting in the y direction. So that'll come with practice. We'll be working a bunch of inclined plane problems. It's a good problem because it helps you to think about vectors in 2 dimensions, and also to think about solving systems of equations, which are important skill for all of you. I said, you engineering students, you'll have a whole class just devoted to this topic, to static forces and dynamic forces, a whole year of classes. Let's work another problem. Oh, this is, pull this up. Remember, we saw the thing where the flying squirrel went through the deal and he fell into the stick. Y'all remember that? We worked those problems right. Well, now we're going to look at what happens right after that, right after the big bunny sort of grabs him by the neck. Well, I say that we are. Can't find it. Well, shoot. I'll have to look for it. It's not really terribly important. Can we just work the problem? That that's less exciting, isn't it? I'm sorry. All right. So in the end of this, uh, you get the situation. I think I have a picture of it. I guess I took it out. You get the situation where you have the squirrel up in the air, and it's like he's flying like a kite. He's like attached to a string where he's being held by the big bunny, and he's like he's flying like a kite. And so if we imagine the forces that are acting on him, I have a couple different forces that are acting on him. Here I'll draw my coordinate system. I have the force due to the string, I'll call this Ft. There's a tension in the string. I have the weight of the guy, Fw, and then I also just have the air resistance. So I'll call this Fa. So we'll call this Fs. Ft is the tension in the string. Fa is just the force from the air or the wind. It's like a kite. And then Fw is just the weight. All right. And I want to know what is the force due to the air? What is this equal to? This becomes basically just a vector problem, because if I have these vectors, then I know that Fa, if this is a static situation, which it is, then I know that Fa has to equal the opposite of the vector sum of Fw plus Ft. Right? If this is a static situation, I know that the net force acting on this guy has to be 0, and so the force by the wind has to equal to the negative of the sum of these two vectors. Right? So it really just becomes a vector addition problem where I'm adding up those vectors. Now I can make some assumptions about what are the various angles here. I'm going to say that this angle is 45 degrees. I'll redraw this over here. So I have the weight, I have the tension in the string Ft. I'll say that this is 45 degrees. And you know, the tension on a kite is maybe about 10 newtons, a few pounds. So I'll say that Ft is about 10 newtons. And then I want to find out what is the Fa. I want to know both the angle and the magnitude of the force due to the wind acting on this guy. Let's say that this is a squirrel. It's uh, about 1 kilogram. So our mass is about 1 kilogram, the mass of the squirrel, which would tell us that the weight here is 10 newtons. Y'all with me on this? Follow me? I'm just doing a vector addition problem, and I want to know, when I do that vector addition problem, when I add up these two vectors, then I can find out what is this vector just by taking the negative of it. All right, so I can find the x and y components. Fw, the x component is 0, y component is 10. It's actually negative 10 because it's pointing down. Ft, I used S here, I'll use T throughout. The tension in the string, the x component is going to be 10 cosine of 45 and negative 10 sine of 45. And then if I want to add up these two, I just add up these two quantities. That's going to be 0 plus 10 cosine 45. It's 7, I'll just call it 7 newtons. And then over here it's going to be 10 and 10 sine 45, which will be 17 newtons. Just adding up the x and y components, just like we did in chapter 3. And then if I want to take the opposite of that, I just negate both of them. So I have negative 7 newtons and positive 17 newtons. Those are the x and y components. So if I think about my new vector, I have an x component that's negative 7 and a y component that's plus 17. That tells me that Fa looks like this. And that's going to be opposite the weight and the tension in the string. So I can find the magnitude of Fa is the square root of 17 squared plus 7 squared, dropping the negative because it's squared. And that gives me a value of 18 newtons. And then the angle I can find is just the inverse tan of the y component over the x component. That's 17 over 7. And I get 67 degrees. Notice that I didn't put the negative in here for negative 7. I recommend that you not do that, but you realize that it's 67 degrees below the positive x-axis. And I'll be looking for that qualifier whenever you give vectors the direction for vectors. This is just like we did in chapter 3. It's just sort of framed in the sense of forces, but really just taking the opposite of the sum of two vectors. You could see a problem like that on your test. Hopefully that's a gimme problem. It's an easy one because I think y'all are pretty good on adding vectors. Gotten pretty good at it, right? Gotten pretty good at adding vectors, okay? All right, you'll need to know how to add vectors. It's important for the Newton's laws problems as well. All right. Next time we're going to add in friction. So it'll be very important that you get friction because friction will be on your test, of course, and it sort of complicates the thing because it brings together our x and our y axes, and we'll see friction a lot through the rest of the semester as well. But I think we'll just call it in there, and I'll see y'all on Wednesday, okay? Y'all hang in there. I know it's a rough time of the semester, like you're having lots of tests, and you're sort of ready for the break and all that, but y'all just hang in, keep chugging.